In this fourth tutorial of this series of videos, we are going to be calculating the phase of the planet for each of the observations that were made by the spectrograph instrument, and we are going to be using all the data we stored previously to achieve this. From this, we'll be able to deduce which of the observations correspond to a transit of the planet. And later on, with this information, we'll be able to calculate the master out and visualize it on a plot. So if you haven't yet watched the previous three videos, I strongly recommend you to watch those first in order to keep on with what we are doing. Okay, so we are going to start by importing some elements of the previous code. So we are just going to copy. We're going to take some of this information you have, the dictionaries basically. So we're going to copy this. Yeah. And we paste it here. Right. Okay. So here we have, we can hide this. It's not very necessary to. We also hide this one. It's not necessary to for the code to print this again. So we are going to import some extra modules. So we are going to import. So import astropy.units as u. So we're going to need astropy.units, and we're also going to need another one. So we're going to say import astropy.constants as const. Okay, we're going to need these. We're also going to need to import matplotlib.pyplot as plt. So yeah, already we need that. Yeah, so basically I can just copy this and we paste it here rather than just writing it. Okay, so we need the observation start list, and we'll have to convert it to an array just as we did for the previous tutorial. So I'll just copy this and paste it here. So here we have the observation start list and the observation start array, and we get that from data-dic1. Okay, so we'll just copy the flux list, paste it here, and the error on the flux. That's it. So first let's convert this to an array. So the flux array will be given by np.array of the flux list. Similarly, we can also convert this to an array. So flux error array equals np.array, and we paste the flux error list. Okay, so here we have the flux and the error on the flux. We have the observation stat list. So now we need the wavelength. So similarly to what we did in the first tutorial, we're just going to define the header unit, which is fits.open of the fits file. If you remember, I'll just type it here, files 0. So we'll open one of the files inside this, and we take the wavelength. Basically, the wavelength was the same for all the 52 observations that were made. So we can just open that using the header unit, and here we'll see wavelength A will be HDU 1. If you remember, it was in the second section of the file, and to access that we need to add a .data and then the variable under which it was stored, which was just the wavelength A. So in order to have smooth values, we are going to cut this. So I'm just going to say here wavelength grid, and basically what I will do is I will take these values and cut it. Actually, I'll just take a set of values within, and to do this I'll add these braces, and let's say we'll exclude the 500 first values and the 500 last values. So I can just note it like this. So this means actually cut the 500 first, you throw it out, the 500 last, you throw it out, and we just take what is within those that interval. So here we have all of that. So I'm going to paste the data of the planet associated with the planet. So let's say import data, and I'll just paste it. So okay, here we are. So I've just pasted the data as of the planet, actually all the parameters. We have the period in days of the transit, we have the mid-transit time, we have the inclination angle, we have the mass of the planet, the mass of the star, basically all the information of that planet, all the parameters. We have the systemic velocity and so on. So the first thing we're gonna do, I'll just say here, calculate the phase. So we need to calculate the phase. So we are going to start by creating a dictionary. So I'm going to call it WASP 127. So WASP 127, let's see, data dic equals to an empty braces. So here I have just created a dictionary. Inside this dictionary we are going to store all the information concerning the transit and the phase that we are going to calculate in a few seconds. Okay, so we're going to create a loop. We're going to say for a certain number of elements. So let me just say for dot in zip of a certain of the arrays we created. So that let me just put it like that for the moment. And the first thing I want to put here is the observation start array. So I will copy that and I'll put it here. So the observation start array actually is an array of 52 arrays because we have 52 observations. And the next thing we want to get is the flux array. So I'll copy that and I'll paste it here. And the last thing we want to include inside the zip function is the error on the flux. So I'll copy that also and I'll paste it here. Okay. So basically we have zip of those three. So what we are doing here is we are going to define a set of variables. So the first, let's just call it value. And let's see. So for value in observation start array, for something in flux array, and for a last thing that we are going to include in flux error array. So the second one, let's just call it flux array. So flux array, and the last thing, let's say just error. So for value, flux array, and error in zip all of these. So it means for every array in observation start, for every flux in flux array, and for every error in flux error array, basically perform the line of code that we are going to define. So it's very practical to use zip when we want to we have a set of maybe arrays, and we want to manipulate the three. We want to use information in each of them to do a calculation. It's more practical to use the zip function. So I need to add a colon. Yeah. So for all that, we are going to define the phase, as, so we're going to define the phase as the value, which is basically an array, every array of the observation start. So we are going to say value, and of course our value is in days, so I'll just add a star u dot days. So remember we imported astropy.units, so star u dot d just adds a day there, and I'm going to say this minus, so the observation in days minus the mid transit time, which is this one here, and it's also in days, so I will just say minus mid transit time, and obviously it's in days too. So actually I didn't really have to include it here, but whatever the case, it's in days, so it doesn't matter much, both are in days. You always want to make sure that the quantities you are manipulating have the same units, because in physics quantities have no meaning if they don't have an associated SI unit or any unit, and the units have to be compatible if you have to add or subtract. So all of this divided by the period, which is also in days. So you want to make sure really that the units are compatible. And I'm going to add one last thing here. We want basically our phase to be in to be less between 0 and 1. So I'm going to add a modulo 1. That's how we can achieve that in Python. So basically this will calculate the phase and give us the result as a moduli or as a modulus, which means between 0 and 1. So the next thing we're going to define the angle, another variable. Angle, which is basically the phase. We basically take the phase, and I will convert this to radians, and to do that I will just say dot u star u dot right. So here I have the angle converted to radians. Basically that's just what I've done. The next thing we need here is the radial velocity. We need to calculate the radial velocity for value, for flux array, and for error. So I'm going to say radial velocity equals negative so equals negative RV amplitude, I paste it here, multiplied by the sine, and to get sine I have to say mp dot sine of 2 pi. So to have pi I need to say np dot pi times the angle. So this is how we can calculate the radial velocity. And lastly, we want to define a quantity here, another quantity called the real wavelength. So let me just add it here. So here I'm going to say real wavelength and this is equal to the wavelength R that we have above divided by 1 plus the systemic velocity so 1 plus the systemic velocity gamma, which is right over here. So I'll just copy that and paste it here. And to the systemic velocity I have to add the radial velocity that we calculated above. So I'll also copy that and I'll paste it here. All right. And all this has to be divided by the speed of light. We need to divide all of this by the speed of light. So I'm going to say divided by constant.c. You remember we imported astropy.constant. So, and we want the speed of light to be in kilometers per second. So I'm going to say here .c.2 colon km per second. So basically what this does is it gives us the unit of the speed of light in kilometers per second, essentially, because our systemic velocity and our radial velocity too are in kilometers per second. So okay, undefined name, this is not normal. Okay, wavelength. Okay, all right. So here we go. We have all of that set. So this is how we can calculate the phase, the real wavelength. We can get it using this formula with the radial velocity that we have above, that we have calculated. So basically we have to calculate this for every observation that was made. We need to calculate each of these quantities that we are going to store. So for all of that, we are going to say if, and now this is how we are going to characterize whether the observation was corresponded to a transit of the planet or not. So I'll just add here as a comment, deducing the observation corresponding to a transit of the planet. So we are going to deduce those of the observations that corresponded to that were made when the planet was in transit and when it was not in transit. So we are going to say if, and this is how we can characterize it, 1 minus T14, which is this value here. It's a parameter of the observation. So if 1 minus T14 divided by let me adjust that, divided by 2 times the period, so 2 star P You always want to make sure that the units are compatible. So if that is less than or equals to the phase, and that the phase is less than or equals to 1, remember we calculated the phase as a modulus because we want to have it between 0 and 1. So if the phase lies between these two, essentially, or we need to set another range. So if the phase is within this first range, or if 0 is less than or equal to the phase, less than or equals to T14, the same T14 that we had, over 2p. So I'll just copy that and paste it here. So if the phase lies within these two ranges, so if you calculate the phase and it falls in any of these intervals, then we're going to jump to a new line. We're going to call that parity. Maybe not parity is not a good word. So let's just say aspect, because parity sounds kind of a bit weird. So let's just say aspect equals in transit. In transit. Okay. So basically, if the phase that we calculate falls within this range, we are in transit. Else, we are not in transit. Let me just see here. Transit. So else, we are not in transit. So when you say else, aspect equals not in transit. So here we have like the nature of the phase. Is it in transit or not? So if that is met, we're in transit, else we are not in transit. And then we want to store this aspect with the phase, the radial velocity of the planet, and the real wavelength. So we are going to create a sub-dictionary that I'm going to call WASP 127dic. So I'll just comment here. We store this information in a sub-dictionary. This plus some other information. So if it's in transit, give us the aspect and all other information. And the way we can do this, we can just copy this big dictionary, and inside this dictionary we want to create sub-dictionaries that contain the aspect plus the data associated with that observation. So kind of pragmatic. So I'm just going to add a J here. So I'm going to say WASP disk data disk J equals, and inside here we are going to store all the information that we want. We can start with the phase because it's the first quantity that we calculated. So I'm going to call it phase. Close that. And under phase, we just have the phase, which is what we calculated. Another information that we can store is the aspect. Another information we can store is the aspect. So whether it is in transit or not. So what you can also tell us about the given observation is its radial velocity, of course. So if it was in transit, it surely was moving at a certain velocity. So I'll just paste it here and have the radial velocity, which is the radial velocity. I just call it this kind of the same name. What we can also include is the real wavelength. So I'll copy it here and I paste it. The real wavelength. And on that real wavelength, we note it real wavelength. It is a real wavelength. So I just add it there. Shift here. We can also add the flux inside our subdictionary. So flux is the flux. So the information contained in flux, we just call it flux, kind of the same name. And we can also include, what else? Is that all? Let me see. So under flux, basically give us the flux array. So I'll just paste it here. And what other information can we include? Maybe the flux error, the error on the flux. So we can just call that error. We will remember that this is the error on the flux, and it was flux array error, I think. Let us check. Flux error array. So I'll also copy this. And I will paste it here. Okay. So inside our dictionary, we're going to arrange it in subdictionaries containing this set of information. So if the planet is in transit, if the planet was in transit when a given observation was made, we have all of this data with a mention that it was in transit indeed. J has to start from 1. So what this data dict J, is the subdict, and we are going to, and so for all the set of, so for all of that inside zip, we want it to be done, and then we raise the value of J by 1 unit. And we can see print, we can print that out. We can print the dictionary to visualize what it looks like. All right. We have this set. We are going to see what it looks like. Let's run this. And okay, we have an error code. Too many indices for array. Array is one-dimensional, but 2 were indexed. Yeah, actually. Okay. Yeah, I think I figured it out. Actually, I put a comma. It's really supposed to be a colon. It's just an error in the syntax. Yeah, so let's run this again. Should be okay. Let's see. All right, that's okay. Not in transit. Let's check this. Okay, not in transit. In transit, okay. So we have some of them in transit, as we're expecting, and we have some others not in transit. Of course, it's about normal. Not all of them were in transit. Okay, this one, for example, is not in transit, not in transit. Okay, so as we can see, some of them are in transit and others are not. So we are going to calculate, so I'm saying calculating the master out. The sum of the flux of all the observations in transit. Not in transit, I mean. So the master out is the sum of all the observations not in transit. So we can just give that a name. Let's see, sum flux. So since it's the sum of a flux, so this variable, it's empty, it has a 0 value, so we are going to say sum flux equals none at the beginning. So we'll see for sub-dictionary, so for sub-dict, well, maybe you can just add, well, it doesn't matter. So for sub-dict in WASP, you can just so for sub-dictionary, inside this dictionary, I'll paste it. So for sub-dict in the dictionary, the sub-dict are where there was data dict J, if you remember. So for sub-dict in the dictionary, we're going to say dot values, because we basically want to go inside the values of the dictionary, and the sub-dictionary are the values of the sub-dict of the main dictionary. So for sub-dict in that, we're going to say if the aspect, remember we start the aspect for each of the observations, if aspect in sub-dict, so and sub-dict aspect, let me just write it well, is not in transit, okay. So if aspect in sub-dict and sub-dict aspect is not in transit, what we want to do is to sum the flux. So we are going to say if sum flux is known, because it was known, so let's write that out. If sum flux is known, remember known, which means it's kind of 0, then sum flux, I'll copy that and paste it here. Then sum flux, just adjust it. Then sum flux takes the value sub-dict flux. At the beginning, it would just take the flux for the first observation not in transit, and as from the second observation not in transit, it's going to do the sum. So we are going to write a code that does the sum. So here is that flux here, as you can see. So we are going to say else the sum flux, we're going to say plus equals, which means as from the second, just take the first value and you add it to the second value. So we're going to say sub-dict flux. So basically what you do is each time you see not in transit, add the flux of that observation to the previous one that was not in transit. That's what we are just basically saying here. and we maybe want to print this out. So we're going to say print, let's say master out. So master out spectrum. I want to put, so master out spectrum plus, we are going to name it. So we'll create another variable, another string. So let's create another variable that will take a value of 1 at the beginning. So we're going to call it m equals 1. So plus string m, we concatenate this, plus we concatenate this with another one, a colon, just to make it kind of presentable. And you give us the sum flux, what you got from the calculation. Sum flux. So print master out with the corresponding numbering, and return us the sum flux. Basically, that's what we are saying. So if it is the first one, just say master out spectrum 1. You give us its master out. If there is a third one, give us master out spectrum 3 equals to its sum flux, and so on and so forth. So there is something wrong in this code. We keep having this cross here. So if sum flux is none, not equals to none. So you print us that. And we scale m by 1 unit. Okay. So this is what we can do in order. So we'll try and run this and see what we get. Let's run this. Yeah, and you can see we have a range of master of spectrum. So you can clearly see that we have 16 of those observations in total that are not in transit, and we have the sum of the flux, the corresponding sum. So it means that 36 that were in transit by deduction. Kind of nice. So what we may want to do now is maybe to visualize them. So we'll try to make a plot to visualize this. So we're going to say, let's plot this to see or to visualize. So you may remember from the third tutorial, we saw how we could do plots. So basically it's the same thing. We're going to use matplotlib that we imported as PLT to plot in Python. That's what we use. So we are going to plot this against a wavelength. We have a wavelength grid that we got here, and we reduced the wavelength grid from the actual wavelength here. So we want our sum flux actually to be reduced in that way. So we are going to say reduced master out. We want to make sure that they have the same dimension or the same numbers, because we cannot plot 10 values against 5, for example. So I'm going to say here sum flux, and we'll also cut it, reduce it to the same number as the wavelength grid. So we cut the 500 first, the 500 last, we throw them away, and we take what is in between. That's what we are just doing here. So make sure that we have equal wavelength, we have equal x and y. To plot x and y against x, you want to make sure that they're equal in number. So now we can say plt.figure. Let me shift that up. So it gives us that on a separate plot. Now we can say plt.plot. And here we put our x and our y arguments. So the x argument will be the wavelength grid, of course. I'll just copy it and I'll paste it here. And the y argument will be the reduced master out. Good. We can give that a color. Let's see, green. Why not? Let's just say green. And we can label it, can add a label. Can label it master out curve. So let's just say master out curve. Yeah. Good. Now let's label our x-axis. No, what is happening here? No. What am I doing? Why do I keep getting this kind of weight? So p_x label. Okay, it's okay now. So we are going to label the x-axis. You can just call that wavelength, maybe grid. Why not? And it is in angstrom. And we also do same for the y, plc.y label. We label the y-axis master out. We can just label that master out. It's a flux and it has some unit. So you'll see this master out. Cool. So let's say here plc.show. Well, we could add a title, but well, you can just leave that out. So let's run this section of the code to see what the master out looks like. Here it is. Wow, kind of very beautiful, kind of dense too. Let's zoom in a little. You can realize that it's kind of very dense, so it's but normal. Let's zoom in again. I zoom in again and again. So it's really dense and it's but obvious because we have 16 observations that were not in transit, and here we have their sum. Kind of beautiful curve. I zoom in again. I zoom in again a little. Okay, so that's it. This is how we can, this is a code that can enable us to get the master out, to calculate it, and here is the curve, kind of very beautiful. Okay, so that's it. Thanks for watching, and I see you in the next tutorial.